I'm pretty damn excited for this video because in this one, we're implementing ProGAN from scratch, which was one of those revolutionary papers that was the first pretty much to output these really high quality images. And you know, this is sort of a big project to tackle, to be honest, implementing this in a single video. So what I want to do is just quickly go through how ProGAN works and sort of the essential parts that you really need to know about. If you want more details, because this is going to be I'm going to go through this a bit quickly. I have a 30-minute paper walkthrough of ProGAN where you will understand, where I go through sort of all of the most relevant parts and the implementation details and all of that stuff. So really recommend you check that out if you want more details. But all right, so what was this paper about? What was the key contribution? And the key contribution was progressive growing, right? And that sort of gave the name ProGAN. So normally, you know, what we did before this paper was just to ask it, you know, can you generate a 128 by 128 output image? And if you think about it, it's kind of a challenging task to directly be asked to output high quality images. So what they did is that they started with asking the generator to output a 4x4 output image, sort of a resolution of 4x4. And so we output a 4x4 with the generator, and we trained the discriminator to also be able to distinguish on the same resolution. And then when we sort of see that, all right, the generator has succeeded with this task, let's now up the level. Then we add a sort of a challenging task of trying to generate 8x8 images. And you know, as training continues, represented by these dots here, then the size or the resolution can become greater and greater, all up to the point of 1024. And to me, this is just one of those things that just really clicks and makes total sense, because, you know, this is very similar to how we learn, right? Taking mathematics, for example, you're not asked to calculate gradients or anything, you know, related to calculus on your sort of first day of learning mathematics. You're starting from the foundation, doing simple addition, 1 + 1, and then you are progressively grown, you know, so to speak, into something that is more challenging, and doing more challenging tasks. So that is the main insight, but they also take this one additional step, which is that, you know, we don't only start with 4x4 and then 8x8. When we actually ask it to generate a higher resolution, so for example, let's say we go from asking it to do 16x16 to 32x32, then we also do something that's sort of a pretty clever thing, which is we fade in that new layer. So that layer is sort of very slowly, gradually, very smoothly transitioned into the training process. And so what they do specifically is that they upsample the image using nearest neighbor sort of standard upsampling, and then they run it through a 2RGB, sort of just a 1x1 convolutional layer that just makes it into 3 channels, and then they transition, and then they do this a conv layer which works on this 32x32, and then they do this 2RGB. So they do an interpolation between those two. So maybe we can call this up, right? That is sent out from this one. And then maybe we can call this out. That's worked with this 32x32. So the sort of the result of this is that we will take 1 minus alpha times the upsampled image, right? Just scale factor of 2 upsampled nearest neighbor, and then alpha times out, which is the one that's been worked a little bit with this conv layer. And so this alpha value, right, this alpha is between 0 and 1. And so it starts at 0, and then it's sort of increased slowly during training to 1. So that's why we say that this layer is slowly faded in. All right, and then of course, as all papers do, they have some tricks, a bunch of tricks to make things work a little bit better. And one trick is pixel norm. So this is in sort of replaced, instead of using batch norm, which was pretty much always used before, and I think it still is in some papers for GANs. But so for this one, they use pixel norm, and it's basically ensuring that the feature vector across the channels is a unit vector, sort of unit length. And specifically what they do is that they take some pixel value, a xy, so some pixel value at position xy, and they normalize this by dividing by the mean of the pixel values squared. And so they sum over all the channels. So n here represents the number of channels. And this, I think the implementation might make this a little bit clearer what exactly happens here. But yeah, that's pretty much all what we're doing. We're just normalizing the pixel values. And it's going to be pretty simple to implement. I think it's just one line. But so that is one trick that they used. Another trick they used, which is a bit more difficult to understand. I sat with this and tried to understand it, and I can't say that I completely do. But so, this sort of, let's start with how. So how they do this is that they at runtime, at each forward step, they take the weight that we sort of currently have, and then they do this scale right here, this scale value, which is basically initialization, sort of the constant value that's used in that initialization, except that they do it every forward step. And so for I guess for sort of normal fully connected neural networks, this constant would be the square root of 2 divided by the number of nodes, number of nodes in the previous layer, in layer, L minus 1 perhaps. I don't know, this is kind of bad, but you understand the idea. We take 2 divided by the number of nodes in the previous layer. So, if you would, yeah, so that's sort of what that is. And so for convolutional neural networks, we instead divide by so we take the kernel size, we multiply it, so we take kernel size squared, and then we multiply that with the in channels, and that is the scale value. And so why they do this is because so when we use optimizers like Atom and things like that, they are not very sensitive to the magnitude or the scale of each weight parameter. It's actually sort of more important what the dynamic range of each weight value actually is. So sort of the standard deviation of each weight is important because Atom normalizes dependent on this estimated standard deviation. So what they want to do, what they want to ensure with this, is to ensure that every weight has the same dynamic range. And in this way, they argue that sort of every weight has this equalized learning rate in the way that all of them require the same learning rate. And they sort of mention in the paper that if we don't do this, then it could be possible that some weights require, the learning rate is too high for some weights and too small for other weights. I'm going to leave it at that, and then this is going to be pretty simple to implement, but not trivial, but we'll see that later on. All right, moving on to the last trick, which I'm not going to go through too much, but it's mini batch standard deviation. That's what it's called, and we'll see this in the code. But essentially, what it does is that it takes the standard deviation of the batch, and then it sends that into the discriminator, so that the discriminator has information about the sort of the variance of each value, and then if the discriminator knows that, it can enforce the generator to output more varied images, right? Because if it outputs the same image in each example, then the discriminator will have that information from this mini batch standard deviation. But you'll see more details of how we implement that later on. So the key points of this paper, and were the ones that we just went through. So progressive growing, this is the most important, and I'm not really sure what is most important of these three, but those are three other tricks that they used. So let's also discuss a little bit about the kind of the architecture that they use. So this is what it looks like for when we're done, right? So when it's at 1024 input size. So for example, for the generator, so starting at the top left, we first have some latent vector with 512 dimensions. Then we do a 4x4, this is a transpose convolution to make it to 4x4 resolution. And then they use a 3x3 conv layer with same padding. So every 3x3 conv layer is same padding, and that is sort of the first block. And every activation in between there will be leaky relu. And then after every 3x3, they also use a pixel norm. I think they only use pixel norm in the generator though. They don't use it in the discriminator. But so then they just do an upsample, nearest neighbor upsampling, so that we double the resolution size. And then we do 2 3x3 same padding, and then upsample, and then 2 3x3. So the pattern is quite simple, you know, upsample 2 3x3, upsample 2 3x3, and then follow that formula until we reach the end right here, where we will do a 1x1 convolution to output it to 3 RGB channels. So that is the generator. For the discriminator, it does the opposite. It's sort of a mirror image of the generator in the way that we input RGB channels. We first convert it to 16, and then we do 2 3x3 convolutions, and then we downsample. So downsample with average pooling, stride to kernel size 2, and then we do 2 3x3, downsample, 2 3x3, downsample, and you get the point. One detail to mention here is that this is where they inject this minibash standard deviation. So they sort of inject that as a feature map. So we can see here that it goes from 512 to 513. So it's one additional channel that we concatenate with the input to this particular block. One thing that makes this a little bit tricky is that this is obviously in the end of training, right? This is when we've done all of the progressive growing and all of that stuff. But let's just take an example of where we are. Let's say we're training on 8x8 resolution. Then all of these right here, we can just cross this because this is not going to be used. And similarly for this right here. So if we remove, so we're only working with 8x8 in our progressive growing sort of step, then we're just using these two, and then then we're going to use a 2 RGB right there, right? So the 2 RGB depends on where we are currently at in our progressive growing. So what that means, you know, to be more concrete, is that in between all of these right here, there's going to be sort of a 2 RGB that is specific for these number of channels. And of course, these are we're just gonna throw these away when we're done and when we're sort of at the end, and we're only going to use this 2 RGB right there. But during training, there's actually ones sort of all over between those blocks. And similarly, you know, for the discriminator, it's going to be between all of these ones. But you're going to see more of that, or you're going to see example of that when we actually implement this stuff. But so what are the results of this implementation, right? That's pretty interesting. I guess disclaimer, I did not train it on 1024 squared. I just trained it up to 256 squared because I don't have 8 V100 GPUs, and I got bored after a while. But so what I got, or let's see, first is to the left. This is what they got. So this is their results that I just took from the paper. And then this is this implementation. So the right is this implementation, the left is their result. I do think they got better results. I do not think we're very far away, and I do think that some of the images look really good. Some of the all of these images are cherry-picked You know, I didn't spend much time on this, but I generated like 200-300, and I took the ones that I thought were the best. And I you know, they did the same. Obviously, every paper does that. But so just for fun sake, I also took out 64 random examples. So just to see what it looks like, sort of more realistic, I guess. And you can see that some look pretty good. Maybe, you know, this one looks pretty good. Actually, I haven't looked at these too much. But then you can have sort of ones that look really weird, like this one. What is that? I mean, this one. I mean, there are a lot of ones. And yeah, so you can see that a lot of them look pretty weird. But nonetheless, some look pretty darn good. And I think that was it. So that is sort of the quick summary of ProGAN. If you want more details, look at the paper walkthrough. And what we're going to do now is we're going to start with implementing the model, which is definitely the hardest part of this video. But so we're going to start with the model, and then we're going to implement the training setup. All right, let's get started with the implementation of this. And I just wanted to show you the data set first of all, if you're sort of following along and coding along, which I recommend that you do. We're going to use a Celeb HQ data set, and there's going to be a link in the description where you can download this, or just Google it. I downloaded it from Kaggle, I believe. And you know, it's basically really high quality images, and yeah, so that's what they look like. And so the sort of structure here is that we're going to do the model first of all, and this is going to be, you know, pretty much all of the tricky parts, right? This is the most tricky part. And again, I think ProGAN is more advanced than the previous ones that we've done, sort of pix-to-pix CycleGAN. And yeah, so I guess I'm just asking you to have a little bit more patience with this one, because it can get tricky sometimes. But so let me increase the font first of all. So we're going to import torch, torch.nn as an n, import torch.nn.functional as f, from math import log2. So those are just the imports. And if we look at the network that we took a look at, and let's just look at the generator, we can see 512, 512, 512, 512, 4 times. And then we divide by 2 to 256, divide by 4 to 128, then 64, and then 32, and then to 16, and then we have this 1 by 1 in the end. So we can maybe write up that we have factors, 1, 1, 1, 1, right, 4 of them, then 1/2, then 1/4, then 1/8, then 1/16, and 1/32. I don't know if you say that. 1 divided by 32 anyways. So let me just sort of create a structure of what we're going to do. So we're going to do vs com2d. That's what I'm going to call the equalized learning rate for a com2d. So vs for I guess weighted scaled convolutional layer. And for the other ones, we're going to create a class for pixel norm. So you know, this is for the normalization instead of replacement for batch norm. For sort of making it a little bit more compact, we're going to create a com block. So we're going to create a com block. Then after that, we're going to create the generator. And after that, in the sort of the end, we're going to create the discriminator. And I guess technically, you know, some of you are going to be like, hey, it's not called a discriminator, it's called critic when you use vegan GP. You're right. But, you know, who cares? Everybody gets what we're doing here. So critic, discriminator, same thing pretty much. So for the VS Com2D, maybe this is, let's see. So here we're going to create, and there are sort of multiple ways you can do this actually, but the way that we are going to do it is we're going to do sort of at runtime at the forward part. That's when we're gonna scale it. So here we're gonna send in some in channels, out channels, kernel size 3, stride 1, padding 1, and then gain 2. So gain is for the initialization constant, right? It's square root of 2 divided by kernel size squared times the in channels. So first of all, let's just call super on that, and then we'll do self.conv, just a normal conv2d. So in channels, out channels, kernel size, right, and then padding. So this scale, we'll call it self.scale. It's just going to be gain divided by the in channels, and then times kernel size squared, and then it's going to be all of that, or let's see, right, no, sorry, so all of this, right, squared is going to be on the outside, so then raised to 0.5. And then what we'll also do is that we don't want the bias of this conv layer to be scaled. So the thing we'll do is we'll do first self.bias, we'll do it in the init part of this class, is we'll set self.conv.bias. All right, so we're sort of copying the bias of the current conv layer that's been initialized to all zeros, and then we're doing self.conv.bias equals none. All right, so we're sort of removing the bias, and then we're initializing the conv layer. So we're going to use nn.init.normal, and this underscore here is for in place normalization, self.conv.weight, and then nninit.normal of no, not normal. We're going to do zeros. So zeros for the bias. And then in the forward part, right, all that we're going to do is self.conv of x times self.scale. And then we're just going to add the bias. And to add that to all of the batches, or sort of the examples in the batch, we're just going to do self.bias.view of 1, and then self.bias.shape of 0, and then 1, 1. So, all that we're doing here is just reshaping the bias term so that we can basically add it to self.conv right here. So, yeah, that's pretty much it. And that is vsconv, the equalized learning rate for the convolutional layer. Yeah, so I think, it's not too difficult, I would say, but it can be tricky to understand the theory of that. All right, so let's implement pixel norm now, and essentially, what we're doing now is we're just sort of implementing the building blocks, right? We're starting with vsconv, this equalized learning rate convolutional layer. Then we're doing the pixel norm, then conv block, and then we're going to use those and put it all together in the generator and the discriminator. But for now, let's go back to pixel norm, and this is going to be quite short. So we're just going to do self, we're just going to do super, and then I guess it's not even important. You don't even have to do this as a class. I think you can just do it. Yeah, I don't think you need to do this, but so we're going to set setup.epsilon to 1e minus 8, and then forward, we're just going to send in x, and the thing we're going to return is x, and then divided by torch.square root of torch.mean of every pixel value squared, and then we're going to take the mean across the channels, which is dimension 1, right? Dimension 0 is all of the examples in our batch, and then we're going to do keep dimension equals true, and that is so that we can do this element-wise division. And then in the end, sort of in the division term, we're going to do plus self.epsilon. Maybe it's important to also do a parenthesis, an additional one here. But so it's going to be, no, this is correct. Okay. So this is right. This is inside the square root. And that is it, right? That's pixel norm. So that's all we're going to use for that. Now for the actual conv block. And what we're going to do here is essentially a conv block of 2 3x3, which is exactly what they did, right? If we look back, we have this upsample, and we're just going to do that in the generator's forward part. So the thing we want to implement now is just these two conv blocks, 2 3x3 same padding convolutional blocks, convolutional layers, which is going to be used in the discriminator as well. The only difference between the two is that the discriminator won't use pixel norm, but that will be used in the generator. And that is the only difference between the two. So now we can do the init part, and we're going to send in some in channels, out channels, And we're gonna, specify use pixel norm. We're gonna set that to true as default, and then we'll call super as usual, and then we'll just initialize self-con1 is gonna be vs conv2d, right? Because we're only gonna use equalized convolution layers, in channels, out channels, and then self.conv2 is vs conv2d, out channels to out channels. And then self.leaky is nn.leaky relu of slope 0.2. And self.pn is pixel norm, right? That's the block we just created up here. So then sort of in the forward part, we're just going to do self.leaky of self.conv. And the way that they did it is that they did basically in this way. So self.leaky of self.conv. And then they did self.pixel norm of x. And if self.use pixel norm, else just x. So I guess we need to specify here self.use pixel norm is use pixel norm, and here we can do use pn. So all right, so the way that they did it is that they use conv, leaky relu, and then pixel norm when I went through their implementation, sort of the source code. But yeah, I'm not really sure why they didn't do it just after the conv layer. I couldn't find any sort of explicit reason why they didn't do that. But so then we're going to do self-leaky of self-conv1, sort of conv2, and then the similar thing, use pixel norm again. There we go. And then we're just going to return x, right? So we're doing two conv layers, leaky relu, and then pixel norm if we use pixel norm. Otherwise, we just return x. All right, so that's the conv block, right? All right, we're progressing pretty nicely. What we're going to do now is we're just going to create the init of the generator, and this is going to be, I guess, the more tricky part. Yeah, for sure, this is going to be more tricky. So we're going to send in some Z dimensions, some in channels, and then some image channels, which we're going to set to default to 3. We're going to do super, and let me just also specify sort of what the functions are going to be. We're going to have a fade-in layer, which is going to take in this constant alpha. It's going to take an upscaled image, and it's going to take a generated image. And then also we're going to have the forward, and I think that's it. But let me just make sure. Yeah, so those are the only 3 actually. And let me see what's wrong here. I think it's just because we didn't write anything, perhaps. So what we're going to do is we're going to create an initial one. And the initial one is going to be for this transposed convolution right there. All right, so you can see sort of the pattern in the beginning. The first one at the top here is a little bit different than what it looks like afterwards, right? All of these are sort of the same block, or sort of uses the same structure, but that's not the exact case in the beginning. So in the beginning, that's why I'm specifying self.initial, because what we're going to do here is use a conv transpose 2D to set dimension to in channels 4, 1, 0, right? So kernel size 4, stride 1, padding 0. And this is going to take 1 by 1 to 4 by 4. And that's what we see also right here, 1 by 1 to 4 by 4. And one thing that is, so some of you might be wondering, shouldn't we use equalized learning rate for the transpose convolution? And you're completely right if that's what you're thinking, because they used equalized learning rate for everything, which I guess is only for the conv layer and the transpose conv layer, because that's all they use pretty much. But I'm gonna cheat, and I'm not gonna implement this in sort of a weighted scaled transpose convolution. And so what I'm gonna do, and this looks really weird, I don't know, I'm not really exactly sure why I did this, but it works. So I was thinking, all right, let's just not do that because it's annoying, and it's only for one layer, so how important can it be? So what I did is that I instead used the pixel norm in the beginning to normalize it before the input to the transpose convolution, and then a leaky relu and then vscom to the in channels to in channels, kernel size 3, stride 1, padding 1, and then again a leaky relu, and then pixel norm. So that is what I did in the initial one, and I guess, you know, the only difference is that this right here, if you want to be completely correct about the implementation, this should be a weighted scaled transpose. But it works, so I'm happy with it. There's something wrong here, so what is the error? All right, so I think I found the error right here. There's, I guess, an indentation error, but now we're good. So now it's nice and clean. So yeah, so I guess after that, right, we want to have an initial RGB, so to speak. So we're gonna run it through this, and then in between here, right, if we're just generating 4x4, then we want to have this this initial RGB to convert this 512 to RGB. So that's what we're gonna create. So this initial RGB is going to be vscom2d, and it's going to take in channels to image channels, kernel 1, stride 1, and then padding padding 0, which is default. And then we're going to create those sort of progressive blocks. So we're going to do prog blocks and then self.rgb layers, and it's going to be an equals and then module list, like this, and then another and then module list like this, and we're gonna set this self.initial RGB to this RGB layers in the beginning. And this sort of the reason why we add this initial RGB here is because we have this initial right here, so there's gonna be sort of I guess one more in RGB layer, because we don't have this inside of the prog blocks. So, you know, directly after there's going to be initial RGB, then prog blocks, initial RGB, prog blocks, and if you just count that out, it's going to be one additional one. I guess that'll make more sense perhaps in the forward part, and you'll see how it looks like, how we'll use that. But we'll just add that to a modulus for now, and then essentially we're going to go through this factors that we set up here, so to create these prog blocks. So we're going to do for I in range of length of factors -1. And the reason why we specify, why do I get, so let's see. Yeah, okay. All right, so the reason why we do -1 is because we're sort of going to take factors of I to factors of I plus 1. So this +1 to ensure that we don't you know, sort of index outside of this list, then we're going to do -1. So yeah, the sort of the conv in channels is going to be integer of in channels times factors of I. So right, because we're in factors, we're specifying exactly how much we should divide the channels with. Right, in the beginning, it's going to be just 1, 1, 1, 1. Then it's going to be 1/2, which is going to take it to 256 channels, and so on and so forth. So that's the in channels. The conv out channels is going to be int of in channels times factors I plus 1. So yeah, this is sort of the in channels, and then we're going to do self.progblocks.append a conv block of conv in channels to conv out channels, and then self.rgb layers.append vscom2d of conv out channels to image channels kernel 1 stride 1, and that is it. So that is all that we're going to do for the generator or the init part of the generator. So now we've created all the prog blocks, all the RGB layers that we're going to need during progressively growing the layers. Yeah, so for the fade in is going to be pretty simple, and all that we're going to do here is just return torch.tanh. And the reason why we're doing tanh is because this is going to be sort of the output, right? And we want the values to be -1 and 1, and that is what it is for the generator. So it's going towards the 10h. We're going to do alpha times generated plus 1 minus alpha times the upscaled. And that's it. So I guess pretty simple there. For the forward part of the generator, we're going to do out is self.initial of x, right? Now it's going to be 4 by 4, right? But additionally to the forward part, we're also going to send in alpha, and we're going to send in steps. So the steps that we're sending in here to the generator is if steps is equal to 0, then we're going to have 4 by 4. If steps is equal to 1, it's going to be 8 by 8. And then you get the point, right? We're going to double at each of the steps. So if if steps is equal to 0, then all we want to do is run it through this initial RGB, and we're done. So the way we do that is just return self.initial RGB of out, right? So if it is step 0, then that's what's going to happen. Otherwise, we're going to go through for step in range of steps, right? So we're going to do that many steps that we send in as steps, which means how many progressive blocks we should run it through. So before we run it through the progressive blocks, we need to upsample, right? We upsample, run it through a block, upsample, run it through a block. So we're going to do upscale is f.interpolate of out, scale factor of 2, and then mode is going to be nearest neighbor. And then for the actual output, we're going to do self.progressive blocks of step, right? And then of upscaled. So we're upscaling it, then we're running through the progressive block that corresponds to that resolution. Yeah, so the what we're going to do at the end is we're going to do final upscaled, right? Because we want one that is at the end, the final upscaled one and the final out, and then we're gonna fade those in and return it. We're gonna do final upscale is self.rgb layers, and we're gonna take of steps -1 self-step -1 of upscale. So the RGB layer is just working one behind all the time, and in that way it's always going to be the same number of channels. So in this case, when we've changed the number of channels, then it's still working on the RGB from this one, and then when we're here, it's working on the RGB from this one, which is 256. So in that way it's always going to work. And then for the the final out, that is going to be self.rgb layers of steps, because that one is the the correct one, right? And then we're going to do of out. So all we've done here is just run it through both of them through a 1x1 comb layer to make sure that they are both RGB channels. And for the final thing, we're going to do self.fade in of let's see, what was it, alpha, so the constant value, final upscaled, right? So this is this thing, and then we're gonna do the final out. All right, so this is the entire generator for the progressive GAN. So the thing that we need to send in later on is these steps, which is the current resolution that we're working with, the alpha value, which is going to be fade in slowly during training, and then the image, right? So moving on to the discriminator, we're going to first create an init, and the thing we're going to send in here is pretty much similar as before. Set dimension in channels, and then image channels equals to 3. And let's just do super init and then pass. And the thing we're going to implement as well is define fade in. And so this is going to be similar as before. And then we're going to define mini batch std, and then that's it, and then forward. All right, so those are the things we're going to implement for the discriminator or the critic, whatever. Yeah, so first of all, we're going to do self.prog blocks. And remember, the prog blocks are going to do it in opposite ordering this way, right? we're instead going to downsample instead of upsample, but otherwise it's pretty much going to be the same. Then we're going to do RGB layers, and then module list, and then module list, and then self.leaky is nn.leakyRelu, slope of 0.2. And yeah, so one thing that might be a little bit tricky here is that obviously for the generator we iterated through these factors, right? And we're going to do the exact same thing now, but the thing that might be sort of tricky is that we're going to work the other way around, right? So we're going to iterate through the for loop from the back of the factors list. So the thing we want to sort of start with is taking RGB to in this case, 16 channels, right? That's what we see up here. So it's sort of the inverse of the generator in many ways. So for that, we're going to do for I in range of length of factors, right? -1. But that is what we're going to start at. And then we're going to move to 0 with a step of -1. So I guess the conv in channels, it's going to be int of in channels times factors of I. And then we're going to do conv, let's see, conv out C is going to be I -1, right? Because we're going the other way around now. And then self.problocks.append conv block of in channels, out channels, use pixel norm to false. And that is the, I guess, only difference. So out channels, we should, no, let's see, this is not correct. This should be conv in channels. It should be conv out channels. Did I do the same mistake over here? So in the init part, no, this seems correct. Hopefully. All right. So we're going to do prog blocks and then self.rgb layers dot append. Let's see, vs conv2d image channels to conv in C, and then kernel size 1, stride 1. And yeah, that is it for those. So now that is all the sort of the progressive blocks. But what we want to have as well is, similarly as we did this initial block in the beginning, we're going to have the same at the end here. And the reason why we're going to have this is because we're going to have this 4x4 conv, which is not inside of our conv block. And so we're going to create the same thing as we did before. We're going to do self.initial RGB. That is going to be a vs conv2d. That's going to take, let's see, it's going to take, in this case, it's going to take image. What is wrong here? There's something wrong with the indentation every time. So this should be correct. Image channels to, what is it, in channels. And then, so, all right, so I just noticed that, this is a little bit confusing. Why is it called initial RGB? And the reason I think I called it that is because it's mirror of the initial RGB of the generator, which means this is what is going to work for the sort of this thing right here for the 4x4 resolution. So for the 4x4 resolution, we get input as 512 channels. And so what we want to do, or sorry, rather, yeah, we get output RGB always from the generator, but we want to map that to 512 channels. So that's why we're taking image channels to in channels, and then we're going to specify kernel size to be 1, stride to be 1. And that is it for the initial RGB. Confusing name, it's just for the 4x4 resolution. So this is for 4x4 image resolution. And then we also got to do an average pooling, which is an average pool. And this is the downsampling. So stride kernel to stride of 2. And for the block for 4x4 resolution, we're going to call this the self.final block. And this is going to be an unsequential, which is going to just take in an vs conv2d of in channels. But we're going to do in channels plus 1, right? Same as it was here, 513, which is in channels, 512 plus 1, 2 in channels, kernel size 3, padding 1, and I guess, stride 1 as well. Then in between that, we're going to have a leaky relu, slope of 0.2. Again, vsconv conv2d of in channels to in channels, kernel size 4, padding 0, stride 1, and then leaky relu, and then in the absolute end, what they used is a linear layer, but I don't know, I didn't want to use that, and I think it's the same thing, right? Pretty much the same thing, at least, of using in channels of 2, 1, kernel size of 1, padding 0, stride of 1. In fact, isn't that pretty much the exact same thing? I think that should be the exact same thing. There should be no difference from how I understand this. Then this should be exact same. But the way we're doing it here, just using vsconv2d, we don't have to do a vs linear, layer. So this is nicer in that way. All right, for the fade in, we're going to return alpha times out plus 1 minus alpha times downscaled. And we need to send those in, obviously. Alpha, downscaled, and then out. So this is what is out from the conv layer, and this is from what is out from the average pooling. But so that is it for the fade-in layer. For the mini batch, we're going to first compute some batch statistics. And so this is going to be towards a standard deviation of x, dimension 0. So what will this give? Well, it will give the standard deviation for every example of x. So this will, I think this is right at least. So if we have n times, let's see, times some channels, times some height, times some width, it's going to give us just n, right? So it's going to give us the standard deviation across all of those right there. And then what we're going to do is we're going to do dot mean. So we're taking the mean value, which will give us what? Just a single scalar value, just a single scale value. And then we're going to do dot repeat of x shape of 0, 1 channel, x shape of height, x shape of, sorry, is it height or width, or is it width or height? I think it's height and width, right? I always get confused over that, because if you, like when people write things, like it's a 4K resolution, 3840 times 1080, is that how it is? That is the width, right? And this is the height. But here, I think we're doing it the height and then the width. Hopefully someone can clarify that for me. I'm feeling a little bit confused over that, but you get the idea. We're just sort of repeating it for the same that is in the x value, right? So we have this single scalar value. We're repeating it to be the exact same, except it's just going to be 1 channel. And so the thing we'll do then is just return torch.catenate of x and the batch statistics along dimension 1, right? So we're concatenating it along the channels, which will, which we looked at for the sort of will give us 512 to 513. Yeah, so that's it for mini batch standard deviation. Now for the forward part. All right, and this is, I guess, the tricky part. We're gonna send in x, send in alpha, and we're gonna send in steps. Again, so what we're gonna do here is if steps is equal to 0, then we are going to, this is for 4x4. If steps is equal to 1, it's for 8x8, and so on. So that's what we're going to send in sort of when we actually train the model, right? Now, one thing that's tricky is that in the appending right here. All right, so I also had to take a quick little break and review this because this can be kind of confusing. So what we're doing here is we're appending the first ones that we're appending is for the highest resolution, right? So the first one is for 1024, 512, etc. And the last one will be, I guess, for 8x8 because we have this final block here for 4x4 resolution. So the thing we're going to do down here to sort of index correctly, right? Because if steps is 0, then we want to do 4x4. If steps is 1, then we want to do 8x8. But as we just said, the last one in that list, right? Not the index of 1, the last one, that is for 8x8. So the thing we're gonna do here, and you know, some of you are gonna be like, is there no better solution? Trust me, I tried a bunch of things. I didn't get things to look as clean. And this is sort of the best that I came up with. Of course, if you come up with something better, I'd happily merge your pull request. But so the current steps is going to be the length of self.progblocks minus steps. All right. So when we're doing the length, right, we're getting the total length, right? So for example, when steps is 1, right, we want the last one in the progblocks list or module list. So we get the length, we subtract it by 1, which gets us the last index. And now you're perhaps thinking, well, what if the steps is 0? Because then we're gonna get the cur steps, which is outside and index higher, right? And we're gonna solve that by similar way as we did in the generator. But so the first thing, I guess we'll get there in a second, but the thing we're gonna do first is self.leaky of self.rgb layers of current step. Should do current step of x. All right, so we're doing self.leaky of self.rgb layers of current step. And the thing that I missed right here is that we should do self.rgb layers dot append of self.initial RGB similarly as we did for the generator. So we're just appending this one, and then we're using that one right there. So we have one more RGB layer than we do of those blocks. And so to ensure that we don't index incorrectly in the prog blocks, we're just going to check if the steps is equal to 0. Then we're just gonna run it through the minibatch standard deviation of out, and then return self.final block of out, and then we're gonna do dot view of out.shape of 0 minus 1. I'm not sure if this is actually needed, but I think that's just how I did it in the training setup. Yeah, and I guess then we don't have the 1 times 1 and stuff, so this is a little bit nicer. But so, you know, this is solving if it's steps equal to 0. So, you know, so we have steps, right, which we send in. So this is a quick recap, I guess. We have steps, which is, let's say 0, then we want 4x4. And so and that will be the end of this self.rgb layers, right? Because the end is where we have the smallest image size, and in the beginning of that list is where we have the largest ones. That's what we did up here, right? When we did it in reverse order. So the thing we're gonna have right here is that this for the current step, and the current step is gonna be, let's see, the current step is gonna be the length of prog blocks if it's for 4x4. So this, for example, is gonna be, the current step is gonna be just the length of the entire thing if it's for 4x4. Then if it is for 4x4, then steps is going to be 0. So then we will just send it through the minibatch standard deviation to concatenate it, and then run it through the final block. All right. Now, one thing that I guess is a little bit tricky, let me bring up this thing right here, is that remember that we did this fade in between the layers? That is what we did in the end of the generator. But that is what we're going to do sort of in the sort of what we do first in the discriminator, right? So how we do that, if we go back to that again, I guess, is that one is going to run through a 0.5 and average pooling, and then from RGB. The other one is going to go from RGB to this progression blocks, and then 0.5. And so yeah, so keep in mind that figure right there. And let's just do first, let's do the downscaled one. So the downscaled one is going to be self.leaky of self.rgb layers of current step plus 1 of self.average pool of x. So, we average pool, which is the 0.5x. We use RGB layers, and we do it current step plus 1. Similar reason as the generator, because the progressive block might sometimes change this channel. And we solve that by having RGB blocks just one sort of index away from the current one we're at. So that is the downscaled one. For the output one, we're first going to run progressive blocks of current step of out, right? So we're going to run it first from RGB, which is what we did over here, right? Then we're going to run it through the progressive blocks, and then we're going to do average pool. Yeah, then we're going to do average pool, which is the 0.5x that is right there. And now we can do the fade in. So the out is going to be self.fade-in of alpha, downscaled, and out. So those are the sort of the fade-in that we do sort of at the top, right? And then we work our way down. And the way we work our way down is we do for step in range of current step plus 1 to the length of self.prog blocks. And so the reason why we have plus 1 right here is because we've already done sort of the current step, right? That's what we did here when we did the fade in. So that's what we did here for the current step. Then we're doing current step plus 1 up to the length of the progressive block. So remember that as we go up in the progressive blocks, we're gonna make the image size smaller and smaller and smaller until we reach the end, which is 4 by 4. So yeah, and this is gonna be just self.prog blocks of step and out, and then out self.average pool of out. So this is just prog blocks, bring out thing again, 2 3x3 downsample, 2 3x3 downsample. That's all we're gonna do, and in the end we'll do the mini batch standard deviation of out, and then return self.final block out, and then .view out of shape of 0 minus 1. Similarly as we did up here, right? Because in the absolute end is where we get 4 by 4 resolution, and the final block will take that to 1 by 1. So I'm actually going to do just a quick recap of this, because I know that there are a lot of things here, and it's easy to get lost in the details of this. So let's start in it. So we do the progressive blocks and the RGB layers because that we're going to run through all of these blocks right here, which is these 2 3x3 convolutions, and then downsample, 2 3x3 downsample. And then we have the RGB layers, because we're going to have RGB layers in between here, dependent upon the image size that we're at, right? So we need to add that to RGB layers. And then we add these prog blocks in the opposite order. So we assume sort of that the first one is going to be for the largest image resolution, right? And then we work our way down. So the first one here, we start at the top. It's going to be the highest resolution. Then we work our way down, and we do RGB layers, which is going to take some image channels to the in channels that we have. So it's going to take this 3, and dependent upon where we are at, it's going to take us to the in channels that we see right here. So it's the opposite of the generator, which took in channels to some image channels. This is the opposite. Then for the actual 4 by 4 image resolution, we're going to have some initial RGB, which is going to take the image channels to in channels, which is 512. I call it initial RGB because that's the sort of to mirror the generator's initial RGB. I know that this name is a bit confusing, but this is for the 4 by 4 image resolution. We append this sort of the initial RGB, and the reason why we're appending it is because remember that the progression block can sometimes change the number of channels. So the prog block needs to kind of be sort of have one additional one than the prog blocks, and that's why we're appending it right here. And then we have an average pool, and then we have the final block, which is just these VSCOM to the to take it to a single value in the end. All right, so then we have the fade in, we have the mini batch standard deviation, and we have the forward. Now, because we're working at a sort of the opposite ordering, but we still want to maintain that step 0 is for 4x4 input resolution, we're doing the length minus a step, the number of steps. And in this way, we are indexing correctly in that module list. So the thing we do in the beginning is we take the RGB layers of the current step, which let's say it's 4x4. If it's 0, then that's going to be the length of the prog blocks, which is just going to, the end of that one is going to be this initial RGB, which is this one for 4x4 image resolution. So that's the one we're doing right there. Now there's a problem because current step, if we subtract this steps right here and it's 0, because there's a sort of a length, sort of a one length difference between prog blocks and the RGB layers, we can't actually index in the prog blocks if it's actual steps 0. So how we solve this is we just do an if statement. If steps is 0, then just do mini batch and return the final block, and that's it. Otherwise, we want to do this thing right here, which is going to take the right here, right from the current step that we're at. We want to do this fade in between an average pool and then from RGB, and then from RGB and then run it through some prog blocks and then downsample using average pooling. So that is what we're doing here. Here's the downscaled average pool, RGB layers, and then self.leaky. Yeah. All right. Anyways, that's the downscaled. And then the out here is going to be progressive blocks of out. And out here has already run through this RGB layers, right? So then we are, let's see where we are at. Yeah, here. Then we run it through the average pooling, and then we do the fade in. So the fading is going to take in the downscale and the out. All right, when that is done, it's pretty simple from there. We're going to run it through the for loop here, which is taking the current step +1 to the length of the prog blocks. We're doing it +1 because we've already done one over here. We've already done current step here. Then we're doing to the length of self.prog blocks because we want to get, to 4x4 or to sort of the end. So we're doing that prog blocks and an average pool. In the absolute end, we're doing a mini batch and deviation, and then we're doing the final block, and that's it. Hopefully we're able to follow this now. Let me copy paste in a test case. So don't bother too much about this, but I'm going to send in some set dimension. I'm going to send in some in channels, and in the paper, this is what it was. But let's just do, I don't know, 256 and 50 or something. We're initializing the generator and the critic. And one thing I also noticed that we're not using the set dimension discriminator or the critic here. So we could as well remove that. Yeah, but let's just keep it for now, but we're not actually using that. So that would be one thing to kind of clean up. I guess we could do that like this. Yeah. And then we would have to remove it over here as well. All right. So now we're going to go through for each of the image sizes, 4, 8, 16, up to 1024. And we're going to do a test on that one. So we're going to do the number of steps, which is going to be log2 of the image size divided by 4. So remember, if steps is 0, then it's going to be 4x4, which is why we divide by 4 here. And we're doing log2 because it's going to be it's going to double at each step. So then we calculate the number of steps that needed. We generate a torch random of set dimension. We assert that it is the correct shape, which is 1, 3, image size. We run it through the critic, and we assert that the out shape is 1 by 1. And then we just print success at that particular image size. And of course, we've coded a lot of stuff. There's so many details. I'm 100% sure that this is gonna fail. So let's wait for it. And there we go. All right, so I think I found the errors. And it were that, let's see. So it was in the generator somewhere. Here, yeah, so I've already fixed it. But this is what it was before. And to make it into a module list where we can index this correctly, it needs to be a list right there. And so we're just going to do that. And then the other error was that here in vs-com2d, we're going to do padding equals 0. So I kind of mistakenly thought that, you know, when we use convolutional, it's going to be padding 0 by default. But that's not what we set vs-com2d to be. Where we set up here, we set the padding to be 1 by default. So here we actually need to send in padding equals 0. And we need to do that for every sort of, for the same one in the discriminator as well. So when we do this, we need to do padding equals 0. Here we need to do padding equals 0. And I hope those are all of them. So let's just rerun it now and let's see what we get. So we still get the incorrect thing. All right, so I think there's some missing here. Yeah, all right, so first of all, this looks a little bit weird. Let's do stride 1 and then padding. Right here, it should be padding equals 0 as well. And I think that is it. I'm not sure why we get this. Oh, right. Okay, we did the same thing over here. All right, so that's the way it should be, but I think we're missing something else as well. So we're doing vs-com padding 0 for the generator. We're doing, here we go. So this RGB, initial RGB, should also be padding equals 0. So let's rerun it and let's see. All right, and it looks good. Success at 4, 8, 16 up to 1024. That's what we like to see. Success, baby. All right, so we've done the model now, and this is the most tricky part. I'm telling you, you know, it's going to be smooth sailing from now. So much smooth sailing. So what I'm going to do actually also is I'm going to copy paste into files. So the ones I'm going to copy paste are sort of the config file and the utils file. So, you know, the config file, we're going to specify start train at image size, let's say 4. If you were to continue training later on, you can change this. The dataset we're going to use is celeb HQ. That's the folder name that we have right here. We're going to have a checkpoint for generator and critic, device CUDA, save model true, load model. We're going to set that to, let's set that to true. Learning rate, because I'm going to take the pre-trained weights to make sure that it works. Or perhaps maybe we can do false here. And then learning rate 1e minus 3. Batch sizes, I'm just going to set it to this, but change this depending on your VRAM. Image size 512, that's what we're going up to, I think. And then channels image 3, set dimension 256, in channels 256. So the paper used 512 here. I used 256, and as you saw sort of in the beginning of the video, we still got pretty okay results. But we could perhaps even get better if we doubled this. But it just takes a lot of VRAM, so that's the reason. Lambda GP is 10, and then number of steps. Not really sure I use this. And then progressive epochs, we're just going to do 50 for every image size, I guess. Maybe we can do it a little bit shorter, maybe 10. So in the paper, they specified that they want 800,000 update steps when they increase alpha, and then 800,000 update steps when alpha is 1. But as I mentioned in the paper walkthrough, I think they sort of they used a batch repeat. So the number of update steps, so this is actually incorrect. In the paper, they said 800,000 sort of real images that they saw, but for each image that they saw, they did 4 update steps. So they sort of used a batch repeat. So that is to say that this batch size can vary, and you should check what you need. Sort of when you think the results are good, then increase the number of epoch, or then increase the resolution. We'll also have some fixed noise so that we will see the improvements made, and num workers to 4. The utils file is just some so that we can plot to TensorBoard. I have video on that. Gradient penalty, I have a video on that as well for vegan GP loss. Save checkpoint, load checkpoint. Yeah, that's pretty much it. Seed everything, I'm not going to use that, so we can remove this part. And then generate some examples. This was just for the beginning of the video to see those examples that we saw. So that's it for those two. Then what we are going to create is a train file. I'm going to do train, and now we're just going to create this stuff. So I'm going to start with import all the imports. So we're going to use torch, optim, datasets, transforms, data loader, summary write for TensorBoard, and then we're going to use those things we saw in the utils file. Discriminator generate from model, log2, tqdm for progress bar, and config. That's pretty much it. And then we'll do torch.backends.cuda.benchmarks cuDNN.benchmarks is equal to true, and this will give us some additional performance benefits. So what we are going to create here is a get loader of image size. So the reason why we do that is because we're going to need a different loader every time we increase the image size. So we're just going to create a function for that. Then we're going to have a train function. And then we're also going to have a main function. And then we are going to have sort of if name equals main. Then we're going to run the main function. So let's see. So what is actually tricky here? I'm going to copy paste in these parts. So let's see. This part right here. What we're doing here is we're getting the generator, and so this is all that we're doing. Initializing the generator that we just created, and then doing the same thing for the critic. And then we're not going to send in this set dimension because we removed it before. Then we're going to initialize optimizers and scalars. And what they did is that they used betas 0.0 and then 0.99, similar to VGAN GP. Then for optimizer critic, they did the same. So yeah, that's it. Then they used a scalar for the critic, then we're going to use scalar critic, scalar generator. And this is just for float 16 training. So that is something just to use as a default, I think. We're going to use a writer to get it in TensorBoard. Obviously, you don't have to do this, but I think it's nice. And then if load model, we're going to load from the checkpoint that we specified in the config file. Then we're going to do generator train, critic train. And that is pretty much it. What we are also going to do is we're going to have a TensorBoard. We're going to do set TensorBoard step to be 0 at the beginning. And then we're going to check which step we're going to start at, which depends on what we set in the config file. So we set start train at image 4. So we're going to do int of log2 of config.start at image size, and then we're going to divide that by 4. So it's going to be 0 if the start image size is 4, and then 1 if it's 8, and so on. Then we're going to do for num epochs in config.progressive epochs of step and then forward, right? That is if you have different number of epochs you want to run for different image resolutions. But yeah, and then we'll specify alpha to maybe be 1e-5 in the beginning. I guess you can set it to 0 as well, but I'm not really sure why I set it to 1e-5, but that's what I did. And then we're going to do loader and dataset is get loader. And here we're going to send in the image size, which is going to be 4 times 2 raised to step. So yeah, we haven't created this yet. And then we can maybe do printf image size 4 times 2 raised to step. And then we'll just do the training part. So I'm going to copy paste that in. Let's see. Now, of course, we haven't done the train function. So I'm maybe going to copy paste in that as well. But so we'll do for epoch in range of num epochs. Yeah, I guess we can print which epoch it is. And then we will run it through the train function, which is going to return alpha and then the TensorBoard step. and it's obviously going to update the parameters of both of our models. So this is what we send in to the train function, which is going to do 1 epoch of training, and then we'll check and we'll save the model every epoch. In the end, sort of going through all of this for loop, then we will do step plus equals 1, which is going to progress to the next image size. So what is left to do is do this train function, and all right, so this is when I copy paste in the train function. We're going to take in the same argument as we sent in over here. Not exactly sure why this is giving us, right, this is because we're not returning anything from the train function, but we're going to solve that. So yeah, I think here I'm going to go actually step through everything because this might be a little bit tricky for some. So we're going to do loop tqdm loader leave equals true. All right, so we'll do the loop, and then we'll do for batch index comma real and then underscore, right? We don't need a target in enumerate of loop, and we'll do real equals real.to conf.to config.device, and then we'll get the current batch size, and that is real.shape of 0, and we'll use that later on. So when we want to train the critic, right, so we're going to train critic, yeah, if you want to actually see sort of the formulas and all of that stuff for this, then I recommend you check out vegan GP video that I've done. But so what we want to do is we want to maximize the estimated value or the expected value of the critic of real minus e of critic of fake. And so, you know, this is similar if you just, to make this into a minimization problem, you just do minus and then parenthesis right there. And that makes it into a minimization problem, which is what, you know, we have for PyTorch. And then let's see here. So what we want to do here, well, let's see, let's bring it back to maximum. I think that's a little bit simpler for me at least. So what we want to do is we want to maximize the difference between those two. So what that means with respect to the critic is that it can distinguish between the real and the fake images. And the way that it can do that is by making this a large number, meaning that the difference between both of these two are very large, right? So, you know, if they are the same value, then the critic can't distinguish between them at all. And then they are actually, you know, 0, which is not what you want to do if the critic wants to maximize it. All right, so we're going to do noise is torch.random normal from normal distribution of current batch size of config.setDimension 11.2 config.device. Okay, so all right, so now we're going to do with torch.cuda.amp.autocast, and we're going to run it. So fake is generator of noise, alpha, and step. So we're sending in the noise here, and then alpha is we're sending in here, and the step we're sending in over there. So when we've done that, we're going to do critic real is critic of real alpha step. Critic on fake is going to be critic of fake.detach. The reason why we're doing fake.detach is that so that we can use this generated image when we're updating the generator in sort of the next part of the training part. So when we're training the generator, so we're doing fake.detach, alpha, and then step, and then GP is going to be gradient penalty of critic. Let me see, real, fake, alpha, step, device, config.device. So I'm going through that pretty quickly because this is copy pasted from a previous tutorial. But so we're doing the gradient penalty, and then the loss of the critic is going to be, again, to make this into a minimization problem, we're going to do negative in front. So it's going to be torch.mean of critic real, and then minus torch.mean of critic fake, right? So then we're doing config.lambda.gp times gp, which is the lambda gp is 10. And then we're also going to add this drift that I talked about in the paper review. This is just to avoid the critic to go too far away from 0. So we're going to do torch.mean of critic real and then squared. So that's the way they did it. Okay, and then we're going to do opt critic dot 0 grad. Yeah, I guess like this, 0 grad, and then scalar critic dot scale loss critic dot backward scalar critic dot step opt critic. Yeah, this is just for float 16 training, which I also have a video on if you're confused over this. So we're just doing this like that. So basically just similar as we do, you know, as normal, right? 0 grad, scale, step, update. All right, so train generator, what it wants to do is maximize E of critic of generator fake, right? Because if the generator, right, it wants to fool the critic. So if we maximize this, that corresponds to making this large, which corresponds to making this a smaller value, which is the opposite of what the critic wants. So yeah, we're going to do the same thing with torch.cuda.amp.autocast. Gen fake is critic of fake alpha step. So we're using the fake that we generated over here. Then the loss of the generator is going to be minus torch.mean of gen fake. Then we're going to do opt critic dot 0 grad scalar gen dot scale loss gen dot backward scalar gen dot step of opt critic scalar gen dot update. And then we want to update alpha. So we want to, you know, fade in this value alpha that we have. So we're going to do alpha plus equals the current batch size divided by the length of the data set, right? So if we do it this way, it's going to be 0 in the beginning of an epoch, and then it's going to be 1 at the end of one epoch. But the way they did it, or the way that I'm going to do it, is I'm going to do config.progressive epochs of the current step times 0.5. So if we say it's going to be 10 epochs of training, then we're going to do half of that is going to be where the alpha is slowly faded in, and then the remaining half is going to be when alpha is 1. Just to make sure of that, we're going to do min of alpha and 1, so that we make sure that alpha doesn't become greater than 1. All right, so I'm going to just copy paste into other things. So here, we've done the tricky part, but this is just, sometimes we're going to generate some fixed fakes, and we're going to plot to TensorBoard, and then we're going to set, we don't need to do this actually. So there we go. We're going to plot to TensorBoard, and that's it for the training setup. And then for the get loader, I'm going to copy paste that in as well, because it's really not difficult. You know, this is sort of more of an advanced video for sure. So I think most of you know this stuff. So here we're doing transforms.compose, resize to image size, to tensor, random horizontal flip, and normalize. And that's just 0.5. The batch size is going to be, let's see, yeah, config.batch sizes. And here we're getting the sort of the step. So I guess you could send that in as well, but here we're just calculating it. For the dataset, we're using image folder because it's already structured in a nice way. And then we're using data loader, where we're sending the dataset, batch size, shuffle, num workers, and pin memory. And yeah, that's it. So, you know, we've calculated, or rather we have implemented everything now, I think. So hopefully, you know, this should be just to train now. But, you know, obviously it's not going to work on the first try. That's impossible. Wait a second. Is this working? Are you kidding me? No, there's going to be an error. For sure there's going to be an error. I can't believe this. Oh my God, I can't believe this. This is amazing. All right, so we can open up, let's see, we're going to open up TensorBoard. So TensorBoard like that. And then let's see, we're going to open up this. And let's see if we get anything. So, right. So we're starting at 4x4. And hopefully, you know, we should get something that looks better than this. And yeah. Actually, it's very slow. I wonder why it's that slow. So it's not, I think the bottleneck is probably the data loading, perhaps, because it's sort of high quality images. So you might have to increase the number of workers, perhaps. Not really sure. That's pretty slow. I think when I did it on 256, actually, that is pretty fast. It took 23 minutes when I did it on higher quality. So let's see what they look like. That is no improvement at all. That's the same image. Are you kidding? It didn't change at all, right? And so I think I know why it's not working, because I made a mistake here, and I'll blame it that I'm tired. So this should be opt-gen, and then this should be opt-gen. All right, because we want to update the generator, of course. So yeah, I'll just rerun it, and hopefully it works now. So I guess I was correct in saying that nothing works the first time, right? All right, so I've ran it for not too long, I guess 3 minutes, and I'm already bored. So what we get here is that it looks like this in the beginning, and then it's, you know, we can see that it's 100% improving, right? It's starting to look like a person, I would say, judging from these 4x4 pixels. But yeah, so you know what I'm gonna do is I'm gonna load the weights that I have already pre-trained, so we'll see sort of what they look like. So yeah, if we go to the config file, we should set load model to true, and maybe we'll change the start trained image to 56. And yeah, and again, this is also going to be available on GitHub, all the code and also the pre-trained weights. So if you want to see that, then do check it out on GitHub. So I'm just going to see now what it looks like. So I'm going to run it on with the pre-trained weight, and we're going to see that they look okay. Yeah, all right. So this is what it looks like when we load the pre-trained weights. You can see some of them look all right. Some of them look not so great. But yeah, just remember that if you're going to run it and actually get something that looks good, make sure you set alpha to 1 here, because otherwise you will only use a small portion of the last layer, or sort of with the fade in with the generator. All right, so that is it. Finally completed this video. This took a long time to make, but hopefully, you know, you got a good understanding of ProGAN. There are probably some details that you weren't able to understand just because I was lacking in my explanations or something. So, you know, this has taken me a really long time to understand. You know, coding this took multiple days, I would say, to get it right. So yeah, you know, this, I guess it takes a while to understand it, but if I could shorten the time it takes for you to understand it, then, you know, that is pretty worth it. And even if you have to go through the code and sort of spend 1 or 2 hours and really understanding ProGAN, then I think that's really, really good. So anyways, thank you so much for watching the video. I really appreciate your support, and I hope to see you in the next video.